Hi everyone, this is Advanced Statistics for the Social Sciences. In this third lecture on one-factor ANOVA, we'll continue talking about variability, and also we'll talk about the F-test and a little bit about R-squared and variability. So we just finished talking about the score decomposition in ANOVA and how we break out a score into the grand mean plus different types of deviations. So we express each score as the systematic component that's due to the predictor and then the leftover error part. We can think about the total variation across all participants, as opposed to just a single score, as being similarly divided into these two components, in the same way that we talked about overall variability, some variability being due to the predictor and some that's left over in the regression framework. This is the same thing for ANOVA. And in the same way as we did with regression, in ANOVA, we're going to use sums of squares and variances to quantify these sources of variability. So this is the formula for the predictor variable sum of squares. And this is essentially to say that we sum all of the scores for a group size n, right? In this example, we have 5 people for a group, that would be 5. And then we take the square of the difference between the overall mean and the group mean. And that's the between group effect of the predictor. So this is the sum of squares for the predictor. This is analogous to the regression sum of squares, but with a categorical predictor, we calculate it differently than we would for a continuous predictor. So here is an example of how this sums of squares for the predictor would be calculated in our smoking example. So we've got the 3 different conditions, and in each condition, we take the conditions mean. For example, the mean for the mean number of cigarettes smoked, the mean smoking intensity for the financial incentive group is 7. So the way we would calculate their sum of squares, which we would then sum with the others, would be to take the group size, which is 5 individuals were in the financial incentive group, and then multiply that by the difference between the total mean of 10 and the group mean of 7 squared, and square that value. And we do that for each of the conditions, and then we sum those, and that gives us the overall sum of squares for the predictor, which here in this example would be 190. Here is the formula for the error sum of squares. So the way that we calculate the error sum of squares is to, for each group, take each score, each observed score, and subtract the group mean, and then square that value and sum those within each group. And so once you've done that for one group, then you repeat for the next group. So for example, for the first part, we can see that in this example, right, we go up to J groups. In this example, we would only have 3, so we would do this 3 times. So we would take the first 5 group, let's say that group 1 is the financial incentive group, we would take a person's observed score, subtract the financial incentive mean of 7, square that, and then sum all of those scores. Then we would do that within group 2 and within group 3, and once we sum all of those, that gives us the sum of squared for the error, the leftover error. So let's look at how this is calculated in our example. So within the financial incentive group, we take each of those individual scores, subtract the financial incentive mean, and then square that difference value and sum those together. In the nicotine replacement group, same thing. We've got the raw scores and then the nicotine replacement mean of 8. And so we've squared all of those differences and summed them. And then in the no help or the cold turkey group, same thing. Individual scores, subtracting the group mean of 15, and then taking those differences, squaring them, and summing all of those values. So within each of those 3 boxes, then we take that number, so we're going to have 3 kind of summations for each of the groups, and we sum those. That gives us that sum of squares for the error. And here we can see that would be 188. So here is where we would identify those values in the ANOVA table that we get here, this test of between subjects effects. So we've got our sum of square for the predictor, which is quit method, and we can see that in the way that it's calculated, it's 190, and then we've got the sum of squared error, and that's highlighted in the blue box. The predictor, sum of squares for the predictor, is highlighted in the pink box. And if we looked at those numbers, we would expect that summing those would give us the total sum of squares. But we could see if we sum those, that those wouldn't give us the number directly in the row directly below error, which says total. But if we summed those, it does give us the number in that corrected total row. So corrected total, the source corrected total, is going to give us our total sum of squares. So the way that we would interpret these sums of squares, the sum of square for the predictor is going to be the sum total variation that's due to the group mean differences. Another way to think about that is that it's the total variation that's due to the influence of the predictor. Okay, so this is the same interpretation of the sum of squares for the predictor from regression. The sum of squares for the error is the total variation in the outcome that is not due to the group differences. So it's the leftover variation in the outcome. Again, same interpretation as we had from regression. And again, as I pointed out in the last slide where we looked at this table, we would expect the total sum of squares to be equal to the sum of squares for the predictor plus the sum of squares for the error. And we will get that information from this corrected total row. So the corrected total sum of squares is going to be 378. That's the total sum of squares that we're working with. Now, the mean squares, or the variance estimates, are the two sources of variability, like the sums of squares, but now we have them on the variance metric. So the mean squares are calculated just as they were for regression, where we divide the sum of squares by the degrees of freedom. And here, for the predictor, the degrees of freedom is j minus 1, where j is equal to the number of groups on the predictor. So in this example, j is equal to 3 because we have the 3 different types of quit methods. So j minus 1 would be 2. And then the error degrees of freedom is calculated as the total number of scores minus 1 minus the degrees of freedom for the predictor, which is 12. Which is 2. So we would have 15 minus 1 minus 2 is equal to 12. So the degrees of freedom error here is 12. And here's where we would find those mean squares in our SPSS output. And then we know from here, the next logical step is going to be dividing the mean square for the predictor by the mean square for the error to get the overall F-test. So here is where we would find the model F-test. And it's in the very first row where it says corrected model under the F column. So that's the value that corresponds to the mean square for the predictor divided by the mean square for the error. And this is going to be our overall model F statistic. So moving on to the R-square effect size. The R-square effect size is, again, it's calculated in the exact same way as we calculated the R-square effect size for regression. And it's still the proportion of the total variation in the outcome that's due to the predictor. So I've shown the calculations here for our smoking example. So it would be 190 divided by 378, which is going to give us an R-square of 0.503. This R-square is telling us, the way we would interpret this R-square is to say that quit method, the predictor, accounts for 50.3% of the total variation in smoking intensity. This concludes the third lecture in the One-Factor ANOVA lecture series. And in the fourth and final lecture on Way ANOVA, we'll discuss Way ANOVA follow-up tests once we've assessed our overall F-test significance.